the words. We'll discuss it. Okay. All right, guys. Today, what we're talking about is in chapter 16.3. And it's pressure. This is on the test one. Yeah. We'll talk about the test later. Okay. Let's get this done for now. We'll talk about this later. All right, guys. Pressure. Well, what causes pressure, guys? Force. We know that force causes pressure. Okay. Anytime there is a force on between two objects, and there's going to be pressure between the two objects. So, for example, if I take my hands and I'm touching them together, okay, there is pressure between there because there's a certain amount of force, okay, that pressure is literally caused by the individual atoms smashing into some other individual atoms. Okay, they have momentum, they smash into another atom, and so they're transferring momentum. So that's how that pressure is caused. These atoms from this hand smashing into atoms from this hand, that causes pressure. If I push harder, okay, then that causes more pressure, right? Okay, so we know if there's more force, then there is more pressure, okay? So the first relationship under pressure we need to know is a greater force yields a greater pressure. However, there's one more thing that's important with pressure, okay, and it's how much space the pressure is exerted over. Okay, if somebody takes their finger and they squeeze and they pinch you, is there really much force there? But it's just two fingers squeezing together. I mean, your fingers aren't really that strong. Okay, I mean, it hurts. Okay, I mean, there's a lot of pressure there because your fingers don't have much. They don't have much space or much area. However, I mean, I could take like this, and I could squeeze much harder with my full hand. I mean, I could squeeze your arm much harder with my full hand than I could with just two fingers. And it wouldn't, I mean, might not hurt as much, right? Okay, so the more space that force is exerted over, the less pressure we have. Okay, so the more area I have, that results in less pressure. But no. But area is the kind of the more. Space is three-dimensional typically. Area is two-dimensional. So I'm just worried about surface area. Okay. So the more area I have, the less pressure I have. Okay. So that what that brings us to, guys, is that pressure is force per unit area. Okay, pressure is going to be measured in pascals, which is abbreviated PA. And a pascal, guys, is 1 Newton per square meter. Okay, 1 Newton per square meter. So in other words, guys, if I take a meter stick here and I draw a square meter on the board, okay, so that would mean one meter this way and 1 meter this way. And I'm... Y'all get the picture? Okay, so a square meter. So 1 pascal would be 1 Newton over this whole area. Okay? So is 1 pascal very much pressure?
Yes.
No. Okay? Because, I mean, this is a huge amount of area. Well, not huge, but I mean, it's much larger than my hand. Okay? And 1 Newton is not much force. Okay? Okay? I mean, a Newton is about 1/10 of a kilogram. So we're talking 1/3 of a pound. Okay, so 1/3 of a pound over this whole thing. So that's not much pressure. Okay. We good so far? All right, so if I take a balloon and I take a paper clip, okay, paper clip, in terms of this little point right here, is that much surface area? No, I mean, that's not much surface area at the point of that at all. So it doesn't take much pressure, I mean, it doesn't take much force on this paper clip at all in order to bust that balloon, okay? I mean, I don't have to push very hard at all, okay? I mean, it's such a small area, okay? Since my area is small, then that creates a very large pressure, okay? Okay, so we can, let me show you a little video here.
You said big force equals high pressure.
And a small force, a small area. So, but the things, the recipe for huge pressure, guys, is going to be big force, small area. Okay, that's what gives us large pressure. All right, so just watch this little film here.
Why do we have to define pressure? When you think of pressure, you think of weather pressure, that kind of thing. Pressure is when two things come in contact with one another, and that force, exerted over that area. So, for example, if you take the nail, go ahead and hang on to the nail, and if we take the balloon, if we put the balloon on that nail right there, all of the pressure of that is pushed right there on that, and so it's no wonder that it pops. Even if you did two nails, so hang on to two nails like that, we're distributing over two nails, and still we have no problem at all. So, here's what teachers can kind of make, or parents can make. They're going to go out today and just going to make it. Here is a board that has little tiny holes in it, and what you do is, it's just a Sunday afternoon. You sit there, what else do you have to do?
Sure.
It says drill. All right, so there you go. So now there's 100 nails that are sitting in there, and this sits here. Okay, you got it? And now, here, let's do this one. The balloon goes on top like this. All right?
Okay.
And now, so that your hand doesn't get hurt, now the board goes on top. Kind of
I got a
like
feeling
this.
what's going to happen here,
You
Steve.
think you know what's going to happen? I think that it's going to come down. It'll be perfect right there. All right, so now watch this. Take your hand and start to push down. And take a look at what happens. All of that weight and that force is being distributed over the entire thing that's there. So we have 100 nails. You can actually look inside and see them poking up inside. That's a tremendous amount of pressure.
Amazing.
Can you see that
Yeah,
right
you can
inside
see
there?
the balloon being pushed up literally inside of it.
In any one nail would pop that. Keep going down. Keep pressing. Keep pressing. See? Now that's a lot of see? That's a lot of pressure.
A lot of pressure.
Yeah.
A lot
Now
of
I want you to get on the bed of nails. So just
It
kind
didn't take a lot of pressure. It was a lot of force. Kind of bad
Isn't that
word.
a fun demonstration? The easy way for kids to be able to see how pressure is being distributed over the entire point. So we realized that somebody who's doing the bed of nails trick, you lay on one nail, you ruin everything. You lay on 5 nails, that's kind of a bummer.
See, I would think about 20 nails, it would pop.
But it's just amazing for kids to see. They can really.
All right. So what we see, guys, is the more area a force is exerted over, the less pressure it has. That's the reason they have those those beds of nails, and you can lay on a bed of nails no problem. Okay, and that's because your weight is exerted over a very large area. Okay, and so that creates very low pressure. Okay. All right. So under the category of pressure, I can have pressure between two solids. A solid could touch a solid, and they can push together, and that can generate pressure. But something else that generates pressure is air. Okay, so I can have air pressure as well. Okay, guys, and air pressure is generated. Air pressure is generated when air molecules are making contact. Okay, so let's just kind of think. I have air molecules. Since it's not absolute zero, that means they're zipping around, right? So since there's millions and millions of air molecules zipping around, you can figure every now and then one of them is going to hit you, right? And so since air molecules have mass, and they're in motion, that means they have momentum. And so if they have momentum and they hit you, that means that they're going to exert a force on you. And so, do you think if there's millions and millions of air molecules surrounding me, they hit me very infrequently? Millions and millions of them all around me. You think they don't hit me very often? Okay. They hit me all the time. Okay, air molecules are zipping around, and they're all over the place, and so they hit you all the time. And so that's what generates air pressure. Okay, air pressure is generated by millions and millions of particles just slamming into a substance, okay? And that's a force, and add up all those forces together and you get air pressure, okay? If I have a tank and I compress the tank, then the way I'm compressing a tank is putting more molecules in there. And if there's more molecules in there, then they're going to hit more often because there's just more of them, right? So that makes higher pressure. Okay. Well, so the pressure in Earth, atmospheric pressure, is around 100,000 pascals. Okay, right around 100,000 pascals. So back up to this square I drew, okay? The 1 square meter. Due to air, right now, since we're at 100,000 pascals, due to air, there is a force on this square of 100,000 newtons. Okay, 100,000 newtons, we're talking dump truck. Okay, so there is the force of a dump truck right now due to air on this square. Okay? So why isn't this broken? No, I mean for real. Right now, there's a force of a dump truck due to air, just due to little bitty air molecules slamming into it right now in this square. Why is the square not breaking in? Because there's the same amount of force on the other side too. Okay? Because I mean there's air on the other side, right? Okay, so there's air pushing this way, there's air pushing that way, and so it balances out. But there's one example where there is not air on both sides, and that's something that we call a suction cup, but we're going to call it a force cup today. And so let's say I have a board here. There's my board, and I take a suction cup, and it's one of those that has a little hook on it. We'll put a hook on it, and I take that and I stick it up to the board. What is on the outside of the suction cup? Air. And specifically, there's air on the outside of the suction cup at 100,000 pascals. Okay? But under the suction cup, when I push it to the board, what happens to the air under it? It gets pushed out. Okay, so is there air pressure on the back of the suction cup? Starts with an N. No. Okay, so no, there is no air pressure on the back of the suction cup. So if I'm looking at it from the side, I'm going to take this and turn it to the side. Okay, here's my suction cup, and here's my little hook. Okay, so I have a large force pushing in this direction. Okay, that's a ton of force due to air pressure. I mean, maybe we'll say it's 500 newtons. Okay, 500 newtons pushing in this direction. However, there's no air pushing in the other direction. So what you're feeling as suction is really air slamming into that thing and pushing it against the board. Okay? If this was a big suction cup, this big square, then it would take the weight of a dump truck to pull this thing off the board. Do I have one? I do. I can go get it later. Yeah, I have one. Okay? So that is due to the enormous amount of air pressure, not suction. Okay? There is no such thing as suction. Anytime that you hear about suction or you're thinking that something is suction, it's always high pressure and low pressure. Okay, so what does a vacuum cleaner do? It doesn't create suction, it... Okay, well, what does the vacuum cleaner make inside of itself? It makes low pressure inside of itself. So it says if I put low pressure inside of me, then that high pressure out there is going to want to come to my low pressure, and so that air, it's sucking the air in. But it's really not sucking anything, it's just creating low pressure. Okay? We also see this effect with tornadoes. So let's say I have a tornado. This is my best tornado drawing. So I have a tornado, and we'll put a little lightning. Okay. So I have a tornado, put a little lightning. and there's a home here, and so inside of the home, I should have air pressure, just normal atmospheric air pressure. But let's say this tornado comes by, and it takes atmospheric pressure, and it drops that pressure by 10%. Okay, if it drops the pressure by 10% instantaneously, then suddenly there's high pressure inside and there's low pressure outside. So what does the air inside want to do? It wants to go out. Okay, so there can be, just depending on the size of the door, there can be up to 10,000 newtons of pressure on a door, of force, on a door due to that 10% reduction really quickly. Okay, 10,000 newtons is a car. Okay, so there could be 10,000 newtons on a door due to that tornado. Okay, so which way do windows and doors typically go in a tornado? Typically outward. Okay. Now, I mean, a wind can blow it in. Okay, but the same thing happens with a home. I mean, with the roof. Okay, if that pressure instantaneously lowers and there's wind blowing under the roof, so now the wind is trying to pick it up and the pressure just lowered, so that's going to take the roof and it's going to. Okay, it's going Dorothy style, right? Okay. To Oz, yeah. That makes sense. Okay, I'm gonna get this thing started up here, and then remind me. We'll come back to this in a second. This is dealing with what we're talking about now, but I forgot to turn it on later. I forgot to turn it on earlier. All right, so this brings us to something, guys, called Bernoullis Principle. Can y'all see that? Okay. Bernoullis Principle. I'll use the color. And according to Bernoullis Principle, guys, if a fluid is in motion, it exerts less pressure on perpendicular surfaces. I mean, parallel surfaces, I'm sorry. All right, so let's say I have a table here and then a fan. And let's say we turn that fan on and so it's blowing air. Okay. If that fan is blowing air, then I know that the pressure on the table, since it's parallel to the direction of motion, is going to be lower than the pressure is over here where it's not blowing. The pressure here, the pressure on the table, since the air is going this way, will be lower than the pressure is over here where there is no air. I mean, no air moving. Okay, here's my thought on it. If you let the air molecules go in whatever direction they want to, then they will, and some of them will smash into the table. However, if I blow them in this direction, then they're going in this way instead of going and hitting on the table. Okay, so that exerts less pressure. All right, so to see this, what I want y'all to do, guys, is take a sheet of paper, and take that sheet of paper and line it up right down, right to the top of your bottom lip. Okay, so I want you to take it, kind of hold it like this, to where it's kind of hold it down, and I want you to line it up right with the top of the bottom lip and blow. Okay, and you want to kind of hang down. And you want to hold it like this. There you go. Okay, hold it like this. Okay, and you want it right here, right at the top of the bottom. So you want the air to go over the top of the air. I mean, over the top of the paper. There you go. There you go. Good. Okay, what we see, guys, is since the air is going on top of the paper, since there's air blowing up here, what happens to the pressure above the paper? It goes down, right? Because there's velocity, so the pressure goes down. Okay. However, under the pressure, under the paper, there is no air motion, and so that's going to be regular pressure. Okay. So therefore, the force on the bottom of the paper that's going upward is much bigger than the force on the top of the paper going downward. So that takes the paper and pushes it up.
So why would you blow with the bottom of the paper instead of...
Okay, so when I blow on, let's say I have it and it's going like that, and air goes that way. Well, see, now this air is not moving parallel to the surface; it's moving perpendicular to the surface, and so this air is really going to smash into it now. I mean, I'm forcing the air to smash into it, so that's going to make greater pressure on the bottom, which is going to push the paper up. But here it's moving parallel, so that's less pressure. Okay, this is the same effect this is the same effect, guys, that... let me go ahead and get this going. Okay, this is the same effect that makes airplane wings work. Okay, in an airplane wing, if I took one and I just kind of cut it, cut it into where you could see the shape of it, it would be shaped kind of like this. And that's really bad, more like that. Let's try again. Okay, it'd be shaped kind of like that, almost teardrop. Yeah. That. If I took an airplane wing and kind of sliced it in half to where you could see the outline of it, okay, then that's the shape it would have. And let's say I took two little air molecules and I traced their paths. Okay, what I would see, guys, is that one air molecule, we'll say this one goes over the top, and we'll say this one goes under the bottom. Which one has a longer path to follow? The top one. So since it has a longer path to follow in the same time, I know that the top one has a higher velocity and the bottom one has a lower velocity. Right? Okay, well, since the velocity is higher on the top, what do I know about the pressure on the top? It's lower. Since the velocity is higher on the top, then that generates lower pressure on the top and it generates higher pressure on the bottom. Well, if I have high pressure on the bottom, then that means that wing is going to get forced upward. Okay, so what I end up seeing, guys, is a net upward force due to the air pressure that's higher on the bottom. Okay? Do y'all need another example, or y'all got that? Okay. There's y'all ever seen those like fertilizing things? Okay. You have here's your hose coming in, and then it's like this little container here, and then you got your down here like a little thing of fertilizer. Maybe it's liquid fertilizer, and then a little sprayer here, and it sprays out. Okay. Essentially, all that happens, guys, is liquid flows through here, but since that liquid is in motion, it generates low pressure, right? Okay, so all the stuff that's down in here wants to come up because there's low pressure. Okay, so you have a little bit of fertilizer down in here. This moving across the top takes that fertilizer and it pulls it out, and then it shoots it into the... Okay, the exact same thing with like a paint gun. Okay, that air is going across the top, it draws up just a little bit of paint and shoots it out. Alright, so come gather around, let me show you all a little something real quick.